So we're coming up to the last session, and the emphasis and focus is on establishing industries. And that is something that I'm deeply passionate about, and where I think that ANFF has an enormous amount to actually offer. So for those who are actually going to be speaking over this next session, and those who have just joined us, I just want to make it very clear that you have 10 minutes to do your presentation, after which there will be 2 minutes of potential questions. I will be asking that question through Slido for those people who have actually got access to that, which you all should have. And I'll ask the question, and that person has 2 minutes to answer it in. Any extra questions we will then provide to that speaker at a later stage to actually follow up with those interested parties. So with that in mind, I'd like to introduce our first speakers, which are Caitlin and Steve from MicroX. They're going to be talking today about portable improvised explosive devices X-ray camera with no need for imaging panel. Please welcome Caitlin and Steve.
Thank you for the introduction. If you haven't heard of MicroX, we are the first company who has commercialized cold cathode X-ray devices. Our first product on the market at the moment is a mobile medical X-ray device, and some of the projects that we're working on at the moment include the MBI Argus backscatter imaging. So my background is I'm the R&D lead. I actually started through a business and innovation grant with Flinders. I was a researcher there to develop the carbon nanotube emitter technology. Caitlin's mechanical engineer and has enthusiastically taken on the lead system engineering role for the Argus device. So I'll talk a bit through our core technology to start with, and then Caitlin will talk about the applications of that and how we're actually using it and intend to use it in the future. So at the back, you'll see an image of a conventional medical X-ray tube there. That's if you get an X-ray of any of your bones in a hospital, that's probably the sort of device that you're going to use to take the image. It's about 25 kilos compared to at the front is our X-ray devices, which are around 2 kilos. And it's all due to the cathode that we've been able to reduce the size and weight and the complexity of it. On the right side is sort of a completed X-ray tube there. We've got the aluminium window at the front where the X-ray beam comes out of, surrounded by lead shielding. And on the left side, we've got a cut open one. What you can see on the left side is the anode, and on the right side is cathode and focusing electrodes. Dive into that in a little bit more detail and how it works differently. So on the left is how a traditional X-ray tube works. If you're not aware, it's basically a tungsten filament, like an old filament light bulb. It's heated up, electrons are emitted from the surface, and they're accelerated towards the anode. The electrons impacting on the anode creates the X-rays. Ours works differently by having carbon nanotubes on the surface of our cathode, and they operate by field emission. In front of that, you see a gate. Gate mesh creates a potential difference between the emitter surface and the area above it, so that the electrons can be emitted out off of the surface. And then again, they're accelerated to the anode, and the anode operates in a similar way. So the analogy that we use is that we've sort of gone to an LED instead of an incandescent light bulb with this. The advantage is we don't need to have oil-filled tube housing to cool down the cathode, and the tungsten filaments in a traditional X-ray tube will typically burn out and need to be replaced in a year or so of operation. So I'll be diving into a little bit more detail on the emitter surface and then the gate mesh as well, as that's what we've developed through various universities and ANFF nodes. These are the emitters themselves. The one on the far left is the one that we use in our current product. It's large compared to most field emission devices that people are researching in other areas at the moment, 20 millimeters by 4 millimeters in size. What we're working on releasing quite soon is a higher powered medical device as well, which is the one in the middle, slightly larger. And then the mobile backscattering one is smaller and circular in size. I have put up a SEM image here of the surface itself. So we basically have a resistive layer and then interdispersed through that whole mess of carbon nanotubes. We haven't gone for a sort of perfectly aligned device like other people do. we focus on having this resistive layer in order to spread the current around when we turn on the device, so that it just shares the electrons between all of our carbon nanotube sites. The mesh, which was developed and is still supplied to us by Macquarie Uni through the OptoFab node, Ben Johnston. On the left, that's about 75 micron thick bars. This is the extraction grid that creates the electric field above the emitter itself. We've found that the geometry and surface of this is extremely critical in shaping the beam path and how the beam basically comes off of the surface of the emitter. The one in the center is what we're developing now for the higher powered medical. It's thicker bars to be able to absorb a bit more of the heat from the electrons that are coming out. And then on the right, we've gone to a more honeycomb style device for the MBI, the Argus, which is hoping to give us a better, a broader field of view imaging. And then just here's a quick snapshot of our manufacturing facility. We're based in Adelaide at the Tonsley Innovation District. We've got a wet chemistry lab with vacuum furnaces where we clean all of our components. Then we've got a class 5 clean room where all of components are assembled and a laser welder within that clean room to weld the tube together. And then we have sort of processing areas where we condition and test the tubes themselves. And then in a separate building, you can see in the top right image is the medical device, or the portable cart. So that's what gets built in the other building with the tube in the other direction. And now I'll pass over to Caitlin.
So I'll tell you a little bit about what we're doing in the future development, as well as what we're doing at the moment, and then focus on the Argus. So at the moment, what we do on the market is our digital radiology. So that's a mobile X-ray cart that is in both the classical medical field as well as deployed in some military hospitals. Then one of the things we're working on is our future checkpoint security. So that is a miniaturized CT baggage scanner where it will enable the passenger to do self-screening. So you'll put your bag in, it'll do a CT image of your bag, it'll do automatic recognition of if there's any suspect devices, and then you'll pass straight through the gate. Another thing we're working on is our stroke imager, which is a lightweight CT imager, which will let you have early on detection of for treatment of stroke. So there's two types of stroke. There's a clot or a bleed, basically. Early on, you want to know which one it is so you can give the right treatment. So within about an hour, if you give the right treatment for stroke, you'll have a much, much higher probability of having no long-lasting effect. So this would enable you to have an image in the ambulance or flying doctor's service to be able to give treatment almost straight away and have a much lower mortality rate. Then focusing on the Argus. So this is something that my team's developing. So at the moment, for identification of IED devices, so explosive devices, the military and the army traditionally use a transmission imaging, which is like your classic X-ray. So you've got your X-ray source, and then your baggage that you're scanning, and then you've got your imaging detector. So this means that your X-rays are going through your device and then hit the detector, and then that's where you're getting your image. So we're proposing instead to use backscatter imaging, where your X-rays are bouncing off the device and going back into a detector that's within the same device. This has a couple of benefits that I'll go through. So it means that it's all within a self-contained unit. So it means that you can go a lot closer to the bag without actually touching it though, not having to reach over it, and it means no separate imaging panel is required. You can still get high enough resolution imaging that you can diagnose down to a component level, although you don't get quite as high resolution imaging as you do with transmission. So this is an image that we took of a prototype actually put onto a robot. So this is one of the main advantages that you've got of it being a self-contained unit. So traditionally, the type of deployment you have is a bomb-suited user who's grabbing this device and taking it downrange to your suspect package. And then they traditionally have to reach over the device, they have to put a panel there and then take an image. And you've got to walk away from that, take the image, and then if you want to take any additional images, you have to go back to it and move it. So by having it as a self-contained device, it means that you're able to mount it onto a robot and nobody has to go down close to the device. And that way you're also able to take as many images as you want from any angle. So it doesn't have to be parallel to any other panel. So you're able to take any image that you want and as many as you want from a safe location. We still can use it as a traditional one. So there is an imaging panel that will be included in the product. So then if you do need that high resolution transmission imaging, you still can do that. But one of the main benefits, this is an image that we've taken, is that you have organics identification. So because of the slightly different spectrum that you get compared to when you're going through something and seeing what's attenuated, as compared to what's reflected off of the object, you end up being able to see plastics and organics instead of just metals. So you still have the ability to see those metals if you do need to do a transmission image, but you're able to see the organic explosives in that IED device. So you've got a lot better ability to diagnose what it is. And as you can still see the other components. You can see the battery, you can see a PCB, a phone and some shrapnel, but then you're able to see that there's explosive with that. So it's a lot easier to identify. And so this is our concept. So this is the MBI unit, and then this is the tablet. So you would have a tablet that controls that device, and it also is able to view the images and do some different things to the images. And then the same tablet would be able to use the transmission panel. We just want to acknowledge that the ANFF and some of the universities have all helped us on the way. So, yeah. Does anybody have any questions?
Good afternoon. Thank you. That was fascinating. We do actually have one question from Rabi, which was, how do you scan large size bags considering the small field of X-ray exposure?
Yeah, so one of the advantages of using backscatter instead of transmission is actually that as you get further back, you're able to widen your field of view. So it works a little bit like a camera. So if you stand really close to something, you're going to get a small field of view. And then as you get back, you do get a lower resolution, but you get a larger field of view. But then the other advantage is if it is mounted on a robot, you can take as many images from different areas as you want to build up an image, and we'll have a stitch function where you can put them together to a larger image.
Can we please all applaud for their presentation, please?